Welcome back to G Fun Facts Online. Today, we are diving deep into a massive discovery in astrophysics that was announced just yesterday, December 5th, 2025. It is a story that fundamentally changes how we visualize the architecture of our universe. Usually, when we picture the cosmos, we imagine galaxies as isolated islands drifting through a dark, silent void. We might think of gravity pulling things together, but generally, we view the large-scale structure of space as somewhat static, or at least chaotic. But a team of astronomers led by the University of Oxford has just unveiled a structure that defies that chaos. They have found a cosmic filament, a strand of the cosmic web, that is spinning. This isn't just a small rotation. We are talking about a structure stretching millions of light-years across, spinning with the precision of a machine. It is a razor-thin highway of galaxies that suggests the universe is far more dynamic and interconnected than our standard models predicted. So let's break this down, starting with the environment where this discovery was made. To understand why a spinning filament is such a big deal, we need to understand the stage it plays on. The universe isn't a uniform scattering of stars. It is organized into a vast network known as the cosmic web. Imagine a sponge, or a 3D spider web. This web has four main components. First, you have voids. These are massive, empty bubbles of space, millions of light-years across, where there is almost nothing. Second, you have walls, which are sheet-like structures that separate these voids. Third, you have the filaments. These are the thick, thread-like strands where the walls intersect. Think of them as the superhighways of the universe. They channel gas and dark matter across the cosmos. And finally, you have the nodes. These are the dense intersections where filaments cross, and this is where you find huge galaxy clusters. For decades, astronomers viewed these filaments essentially as pipes. They were seen as passive conduits that simply carried material into the galaxy clusters. We knew matter flowed along them, but we didn't think the pipes themselves were doing much. That metaphor is now dead. The new discovery suggests these pipes are not just carrying matter. They are spinning, twisting, and imparting angular momentum to every galaxy trapped inside them. The specific structure we are talking about today was identified using data from the MeerKAT survey. It is located about 140 million light-years away. Now, in cosmic terms, that is right next door. This structure is a subfilament, a delicate strand embedded within a much larger cosmic structure. But delicate is a relative term here. The parent filament stretches over 50 million light-years, but the newly discovered razor-thin strand is the real marvel. It spans roughly 5.5 million light-years in length, but it is only 117,000 light-years wide. I want you to visualize that aspect ratio. If this filament were a standard pencil, it would be kilometers long. It is an incredibly thin, blade-like line of galaxies. Finding something this long and this narrow is already rare, as it implies a very organized formation process. But the motion is what has scientists excited. Dr. Lila Jung, a co-lead author of the study, used a brilliant analogy to explain what is happening inside this strand. She compared it to the teacups ride at a theme park. If you picture that ride, you have individual teacups spinning, but the entire platform they are sitting on is also rotating. That is exactly what is happening here. The galaxies are the teacups, and the filament is the platform. Using the MeerKAT radio telescope in South Africa, combined with optical data, the team analyzed 14 specific galaxies inside this filament. They looked at the hydrogen gas within these galaxies and found two synchronized motions. First, there is bulk rotation. The entire filament is rolling like a log in water. They measured this by looking at the redshift and blueshift of the galaxies. Galaxies on one side of the filament are moving away from us relative to the filament's center, and galaxies on the other side are moving toward us. They clocked this rotation speed at approximately 110 kilometers per second. That is a massive structure, moving at incredible speeds. Second, and perhaps even more surprising, is the spin alignment. The individual galaxies inside the filament aren't spinning randomly. Their axes of rotation are aligned with the rotation of the filament itself. This is the smoking gun. In a chaotic universe, galaxy spins should be randomized. For them to be synchronized with their parent filament implies a powerful, organized transfer of angular momentum from the largest scales of the cosmos down to the individual galaxies. This brings us to the physics. Why is this happening? One of the deepest unsolved problems in cosmology is the origin of spin. In the early universe, matter was almost perfectly uniform. Gravity amplifies density fluctuations, pulling matter inward. But gravity pulls radially. It pulls straight in. It doesn't inherently cause rotation. If you drop a ball straight down, it doesn't start spinning on its own. So where did all this spin come from? The leading explanation has been something called tidal torque theory. The idea is that as a proto-galaxy, a cloud of gas and dark matter forms, it gets tugged on unevenly by the gravity of surrounding structures. If a massive wall of matter is to your left and a void is to your right, the difference in gravitational pull can twist the collapsing cloud, giving it a spin. But this theory has limits. It works well for the early stages of formation, but it struggles to explain strong alignments in the mature universe. This new razor-thin filament suggests the relationship is much more direct. The filament itself acts as a spinning vortex. The galaxies born within it inherit this motion, much like small eddies forming in a swirling river. This discovery forces us to reconsider how angular momentum is conserved and transferred across millions of light years. Let's take a moment to talk about the technology that made this possible, because it is a story of innovation in itself. This discovery relied heavily on the MeerKAT telescope in the Karoo region of South Africa. MeerKAT is a precursor to the massive Square Kilometre Array project. It consists of 64 interlinked satellite dishes. Its superpower is its sensitivity to radio waves, specifically the signature of neutral hydrogen. Why neutral hydrogen? Because it is the fuel of star formation and, critically, it is the perfect tracer for cosmic dynamics. Unlike stars, which are dense and compact near the center of a galaxy, hydrogen gas extends far beyond the visible edge. It is fluffy in a sense. It gets easily disturbed and influenced by the gravitational environment. By mapping this hydrogen, MeerKAT allowed astronomers to see the hidden velocity structure of the filament that optical telescopes would have missed. However, optical telescopes did play a role. Instruments like DESI, the Dark Energy Spectroscopic Instrument, and the Sloan Digital Sky Survey provided the map of the surrounding galaxies. They allowed the team to see the skeleton of the larger filament. This combination of radio data for motion and optical data for position is the new gold standard in astrophysics. So what are the implications of this rotating giant? First, it tells us something profound about dark matter. We cannot see dark matter, but we know it provides the scaffolding for the universe. A filament of this size, rotating at this speed, must be anchored by a massive amount of dark matter. This discovery supports the cold dark matter model, which predicts that structures form from the bottom up, small things merging to make big things, but also allows for these large-scale collapses. However, the tightness of this structure creates a problem for our simulations. Most computer simulations of the universe produce messy, turbulent filaments. To get something this thin, this long, and this coherent in its rotation suggests our simulations might be missing some physics. We might need to refine how we model gas dynamics, or even the nature of dark matter itself. Dr. Madalena Tutorare, another co-lead author, referred to this filament as a fossil record of cosmic flows. Because the galaxies in this filament are gas-rich and dynamically cold, meaning they haven't been messed up by violent collisions, they are effectively time capsules. They show us how galaxies looked and moved as they were first being fed by the cosmic web. Looking ahead, this discovery is likely just the tip of the iceberg. If one such spinning filament exists just 140 million light-years away, the universe must be teeming with them. This is crucial for upcoming missions like the European Space Agency's Euclid telescope and the Vera-C-Rubin Observatory. One of Euclid's main goals is to measure weak gravitational lensing, the tiny distortion of background light caused by mass. But here is the catch. If galaxies naturally align with their filaments, as this study shows, they can mimic the signal of lensing. Astronomers call this intrinsic alignment. It is a nuisance if you are trying to study lensing, but it is a treasure trove if you are studying structure formation. Understanding that filaments spin will allow scientists to correct for these alignments, making their maps of the dark universe much more accurate. And when the full Square Kilometre Array comes online, it will be thousands of times faster than MeerKAT. It will be able to map the spin of millions of filaments. We are moving from a static picture of the cosmic web to a fluid dynamic model. We will be able to watch the universe flow, swirl, and evolve. To wrap this up, think about the new verb this adds to our cosmic vocabulary. We often say the universe is expanding. Now we must also say the universe is twisting. From the quantum spin of an electron to the rotation of the Earth, and now to the majestic roll of filaments spanning millions of light years, angular momentum appears to be a fundamental currency of reality. This razor-thin filament is a spinning cosmic highway. It reminds us that we are not static observers on a rock. We are part of a vast, interconnected system, whirling through the dark in a grand, synchronized dance that began with the birth of time itself. As we peer deeper into the web, we can only wonder what other giants are turning in the dark, waiting for us to tune our telescopes to their silent rhythm. That is all for today's deep dive on G Fun Facts Online. Thanks for listening.